Let's solve problem 4-9. I'm going to start by writing down the given. A piston cylinder device initially contains 0.5 meter cube of nitrogen gas. I'm going to consider initial state number 1. Initial volume of gas is given 0.5 meter cubed. It is the volume of nitrogen gas. Initial pressure is given 400 kilopascal. Initial temperature is given 27 degrees C. An electric heater within this device is turned on and is allowed to pass a current of 2 amps for 5 minutes from 120 volt source. So I can solve for electric work. It is equal to voltage times current times delta T, which is equal to 120 volts times 2 amps times 5 minutes. And we know that 1 minute is equal to 60 seconds. And we know that 1 volt amp is equal to 1 joule per second. So electric work, which is the work into the system, will be equal to 72 kilojoule. This is work into the system. Moving on, nitrogen expands at constant pressure. So state 2, I know that V2 is larger than V1 as it expands. P2 is equal to P1, and P1 is given in the problem statement, 400 kilopascal. And we have a heat loss of 2800 joule or 2.8 kilojoule. Heat loss is 2.8 kilojoule. Determine the final temperature T2 of nitrogen. Consider nitrogen an ideal gas and why. Why nitrogen is an ideal gas in this problem statement. From table A1, I can read T critical for nitrogen, and it is equal to 126.2 Kelvin. If I convert it to degrees C, it's going to be almost equal to negative 147 degrees C. So if I compare it with the given temperature, which is T1, 27 degrees C, I see that T1 is way larger than T critical for nitrogen in this problem statement. So I can say that nitrogen behaves as an ideal gas. So I can use ideal gas law in order to solve this problem. PV is equal to mRT. I'm interested in T2. I'm going to write down ideal gas law in state 2. P2, V2 is equal to N R T2. Pressure in state 2 is given. Volume in state 2 is not known, but I just know that volume increases. Mass in state 2, I can solve for it. R is given in the table for nitrogen, and T2 is unknown. So I'm dealing with one equation and two unknowns. In order to solve the equation, the number of equations should be equal to the number of unknowns. So I'm going to need an additional equation. I'm going to use thermodynamics first law. Delta E system is equal to E in minus E out. Left-hand side is E2 minus E1. The energy change inside the system from state 1 to a state 2 is equal to right-hand side E in minus E out, or the energy at the boundaries. Left-hand side, E2 minus E1 is change in internal energy plus change in kinetic energy plus change in potential energy. This is equal to E2 minus E1. I'm going to assume that the system is stationary, so there is no change in kinetic energy and no change in potential energy. This is my assumption. So E2 minus E1 will be equal to U2 minus U1, which is M2U2 minus M1U1. Right-hand side, E in is equal to Q in and out in Q in plus W in plus mass in times enthalpy per unit mass plus kinetic energy per unit mass plus potential energy per unit mass in. So I know that there is no heat that gets to the system. I know there is an electric heater, so we have W in, and there is no mass that gets to the system. So E in will be equal to W in, and I know that W in is the electric work, and I solved for it. It is equal to 72 kilojoule. Moving on, E out, which is equal to Q out plus W out plus mass out times enthalpy plus kinetic energy plus potential energy all per unit mass out. I know there is heat loss, 2.8 kilojoule. Let's see if there is any work done by the system. We are dealing with a cylinder and a piston. So the piston moves, and I'm going to have boundary work. It is equal to P times delta V. So W out is P times the change in volume, and there is no mass that gets out of the system as we do not have any exhaust valve or outlet in the system. So E out is equal to Q out plus P times delta V, and we know that P times delta V is equal to P times mass times the change in specific volume in the system. So I'm going to plug all these terms into the first law of thermodynamics, which I call it equation number 1. So E2 minus E1 is M2U2 minus M1U1 is equal to E in, which is W electric, minus E out, which is Q out, plus mass times P times delta V. So I'm going to clean this. I know that based on conservation of mass, there is no mass gets into the system or gets out of system. So mass in a state 1 is equal to mass in a state 2. I'm going to call it just mass. And I can use ideal gas law in initial state to solve for mass. So it is equal to P1 V1 divided by R of nitrogen times T1. Initial pressure is given 400 kilopascal. V1 is given 0.5 meter cubed divided by the gas constant for nitrogen. I can read it from table A1. It is 0.297 kilopascal meter cubed per kilogram Kelvin, and T1 is given. It is in degrees C. I have to convert it to Kelvin. It has to be absolute temperature, 300 Kelvin. So mass will be equal to 2.25 kilogram. So going back to this equation, mass 2 minus mass 1, which is mass times U2 minus U1 is equal to electric work minus Q out minus mass times pressure times delta V. So W electric minus Q out is equal to mass times U2 minus U1 or delta U plus pressure times delta V. And based on the definition, I know that this is equal to change in enthalpy. So I'm going to have mass times delta H. Because we are dealing with an ideal gas, nitrogen is an ideal gas here, I know that delta H is equal to Cp times delta T, T2 minus T1. So let's see what we have. Oops, sorry. Electric work minus Q out is equal to mass times Cp times T2 minus T1. Electric work, we solved it. It is equal to 72 kilojoule. Heat loss is given in the problem, 2.8 kilojoule. Mass, we solved it. It is 2.25 kilogram. Cp, I can simply read it from table A2, it is 1.039 kilojoule per kilogram Kelvin. Again, this is from table A2. T2, I'm interested in T2, and T1 is given in the problem 27 degrees C. So one equation, one unknown, I can solve for T2. It is going to be equal to 56.7 degrees C.